Yes. In previous video we have studied about the homomorphism and its properties. So today we are going to discuss kernel of homomorphism and its properties. So what is kernel of homomorphism? Let F is a mapping from R to R dash is a homomorphism from the ring R into R dash. The subset K of capital R defined by, see how they have defined, K is equals to X belongs to R, where F of X is equals to 0 dash, and here 0 dash is a 0 element, right? Why we have taken 0 dash? Because R into R dash we have mapping, right? R into R dash we have. So therefore, 0 dash is a 0 element of R dash, I can say that. So therefore, this K is called the kernel of F and is denoted by KER of F. Okay, so this is about kernel of homomorphism. Okay, so you need to remember this mathematical expression of kernel of homomorphism. So let us see how we'll get the homomorphism. If the homomorphism is trivial, then the kernel of F, what will get? See, trivial homomorphism means same thing. So F of X is 0, right? Where every X belongs to capital R. So 0 is 0 element of R dash, right? So same thing but little bit different. Okay, so for the trivial homomorphism, F is mapping from R to R dash, will get kernel of F is equals to capital R. Next note, for the identity homomorphism, so if I choose an identity homomorphism, means it is a mapping from R to R and we are denoting that function as IR. So how they have defined, already we have discussed in the previous video what is IR. Okay, so defined by IR of X is equals to X, right? Then this kernel of F obviously will get a singleton set containing 0 element. So if you observe identity map, how they have defined R to R, right? So according to the definition, IR of X is equals to what? X. Right? So kernel of F, if you observe the definition of kernel of F, F of X is 0 dash or 0, I can say that, right? For every X belongs to R. So definitely we will get this kernel of F contains what? Only 0 element. So therefore what I can write on singleton set, will get singleton set containing an element 0. So these are the notes you need to remember. So now we'll discuss a theorem on kernel. If F is mapping from R to R dash be a homomorphism of rings with kernel K, then, so first condition is K is a subring of R. For every R belongs to R, A belongs to K, AR belongs to K and RA belongs to K. Means it is an ideal. Okay, so we need to show that first case is K is a subring and next K is a ideal. So first condition if you observe, so how the kernel of F we have denoted as K, how they have defined the set f of x is 0 dash where every x belongs to capital R, and 0 dash is an 0 element of R dash, obviously according to the definition. So our ultimate goal is to show that K is a subring. So subring, it means what? We need to show that according to the definition of subring. So two conditions we have, right? So first condition is, if you want to say that a subset, non-empty subset, that too, non-empty subset, if I say capital S of the ring capital R is said to be a subring if two conditions satisfies. What are those two conditions? First condition is, for every A, B belongs to R, for every A, B belongs to S, A minus B is also belongs to S. Right? Next, second condition is what? For every A belongs to S and B belongs to S, A into B belongs to S. Right? That is the definition of subring. So if I want to show that, only the thing is you need to show two things over here for subring. First condition is, for every AB belongs to S, A minus B belongs to S, and for every A comma B belongs to S, A into B is also belongs to S. That's it. So here we have K. So therefore if I take X comma Y belongs to K, then obviously how they have defined the function? F of x is equals to 0 dash. So therefore f of x is equals to 0 dash and f of y is equals to 0 dash we get. So our ultimate goal is to show that first condition, f of x minus y is equals to f of x minus f of y, right? So if I say that if I consider f of x minus y, so this f of x minus y, how I can rewrite according to the conditions of homomorphism? F of x minus f of y I can write down. Already we have f of x value and f of y value, so put that, definitely we will get 0 dash. So therefore for every x minus y, see this x minus y belongs to k, obviously f of x minus y is also belongs to k, obviously, right? So what we have taken, x in comma y belongs to k and x minus y is also belongs to k, we have shown it, right? So why we have written this one? According to the definition, for every x belongs to R, we have f of x is equals to 0 dash. So what we have shown here, f of x minus y is equals to 0 dash. So therefore x minus y belongs to R. So first condition is over. Next again, f of xy, if I take f of x into f of y, will get according to the definition of homomorphism. So f of x value is 0 dash, this one is 0 dash, obviously we will get 0 dash. So for every xy belongs to k, xy is also belongs to k, therefore k is subring, I can say. First condition is over. Second condition, what we need to show that k is an ideal. So for that purpose, what we need to show that for every a belongs to k and for every r belongs to capital R, AR belongs to K. So this is right ideal and this one is left ideal. We need to show that. So let us see how we have shown it. So for example, if I say A belongs to K, right, and R belongs to R, f of AR, right? So f of AR value, what will get it? So according to the definition of homomorphism, I can write down f of AR as f of A into f of R. So f of A obviously will get A belongs to K, no? So according to the definition of K is what? X belongs to R. See here, f of x is equals to 0 dash. So A belongs to, we have taken, right, K. So therefore obviously it is like this, f of A is 0 dash, I can write. So 0 dash. But R is belongs to R, so therefore I have written as it is, f of R. So 0 dash is an 0 element. So 0 into anything is 0, therefore we'll get 0 dash only. So therefore f of AR is equals to 0 dash we got. Obviously I can say that f of AR is equals to 0 dash we have. So obviously I can say that AR belongs to K. Similarly we can show that f of RA. How? Consider f of RA, right? Same thing, A belongs to K and R belongs to R, right? F of RA. So f of RA, how I can write down? F of, according to the definition of homomorphism, f of R into f of A, I can write down, right? So after this, already we have f of A value as what? According to the definition of set K, how they have defined f of A as 0 dash. So f of R into 0 dash is nothing but 0 dash. So f of RA, what we got? 0 dash. So 0 dash means K is what here? F of x is 0 dash. So we have assumed that f of RA. So what we have taken here? F of RA. F of RA is equals to 0 dash we are getting. It means RA is belongs to what? K. So this is how we need to show that K is a ideal. So therefore from equation 1 and 2 I can say that kernel F is an ideal of R. So this is the procedure to show that R is a, K, kernel is a subring and kernel is an ideal. Okay. So next we move on to the next theorem. So F is a mapping from R to R dash be a homomorphism of rings R into R dash with kernel K. Then what they are going to show that F is 1 1 if and only if K is containing C intercept C. Right? So let us show that condition. We need to use these conditions, homomorphism condition and kernel K condition. Then we need to take F is 1 1 and we need to show that K is equals to singleton set containing 0 element. So let suppose F is 1 1, let F be 1 1, and if I take A belongs to K, according to the set K, what I can write down? F of A as 0 dash I can write down. So f of A is equals to f of 0. Why? Because we have f of 0 is 0 dash, right? F of 0 as 0 dash implies we'll get, this is also we'll get from homomorphism, properties of homomorphism, right? So f of A is equals to f of 0, f of 0 is equals to 0 dash I can put. So this implies f of A is equals to f of 0. It means what? The element A is equals to 0, right? So f of A is 0 dash and f of 0 is 0 dash. So that is what A belongs to K. What we are getting, if A belongs to K, f of A what we are getting? 0 dash. What we have? 0 dash, right? So similarly what we have, f of 0 is 0 dash, right? F of 0 is 0 dash. So 0 dash, here also 0 dash. So I can equate these two. That is what f of A is equals to f of 0 I can I can write down. So after this, so for every a belongs to k, we got f of a is 0 dash. Obviously we'll get 0 is belongs to k, right? So that to how a is equals to 0. So therefore k, directly I can write down k is containing a singleton set containing an element 0, right? So next, conversely, if you observe, we need to take k as containing a set containing a single element 0. So if I take f of a is equals to f of b, right? If I take f of a is equals to f of b, then how I can write down f of a minus f of b is 0 dash. So obviously f of a minus f of b, how I can write down f of a minus b, because f is homomorphism. So f of a minus b is equals to 0 dash, it means a minus b belongs to k, right? So a minus b belongs to k means k is what we have taken it as 0, only single element. So a minus b is equals to 0 I have written. So therefore what I can write down, a is equals to b. So a is equals to b according to the definition of 1 1, right? Every element of the set A is mapping with the every element of set B. So that is what A equals to B. So therefore f is 1 1, I can say that. Okay. So this is how we need to show that if f is 1 1, we have shown that k is containing a singleton set containing 0 element. And conversely, what we have done, we have taken a singleton set containing 0 as k set, and we have shown f is 1 1. Okay. So next theorem, let f is a mapping from R to R dash be a isomorphism of ring R onto R dash. Then, so already we have discussed what is isomorphism. First it should be a homomorphism. After that the given function should satisfy f is 1 1 and onto. Then we can say that it is an isomorphism. The given what I can say that function is an isomorphism, I can say that. So here they have given f is a isomorphism, and first condition what they given, if R is a commutative ring, then R dash is also commutative. We need to show that. Next, if R is a without 0 divisors, then R dash is also without 0 divisors. So 0 divisors means we have already discussed in the class. So 0 divisors, when we are going to say that 0 divisors, R is having a 0 divisors, for every AB belongs to R, A is non-zero and B is non-zero, then their multiplication A into B is equals to 0 we should get. That is 0 divisors. But without 0 divisors means, apart from that condition, I can say that it is not having 0 divisors. So if R is a ring with identity, then R dash is also with identity, right? If R is an integral domain, then R dash is also an integral domain. If R is a field, then R dash is also filled. We need to show that. So let us say first condition, if you observe, what we need to show that R is a commutative ring, we need to take, and R dash is also a commutative ring. So let us say A dash B dash R belongs to R dash, obviously, right? Why? Because f is mapping from R to R dash, right? So what we can take, for every A belongs to R, this implies f of A is belongs to what I can write down, R dash, right? So f of A, I can rewrite this term f of A as A dash, I can write down A dash belongs to R dash. right? Same thing we are considering over here. So therefore A dash belongs to R dash and B dash belongs to R dash we have taken. So there exists AB belongs to R, obviously. So such that what I can write down, f of A is equals to A dash I can write down, f of B is equals to B dash, because f is onto, right? So consider why it is onto, because f is isomorphism. So therefore I can apply the condition of onto. And also we have shown you f of A as A dash I can write down, right? So therefore if I observe, so commutative ring ಅಂತ ಹೇಳಬೇಕಾದ್ರೆ ಏನಂತ ಪ್ರೂವ್ ಮಾಡಬೇಕು, ಓನ್ಲಿ ದ ಥಿಂಗ್ ಈಸ್ ವಿ ನೀಡ್ ಟು ಶೋ ದಟ್ multiplication, under multiplication A into B is equals to B into A. If I show that, then I can say that R dash is a commutative. So here we have taken element A dash B dash, because why we have taken A dash B dash, our ultimate goal is to show that R dash is a commutative ring. So therefore we need to take the elements from the R dash and we need to show that R dash is a commutative ring. So therefore we have taken A dash into B dash is equals to f of A into f of B I can write down. So f of A into f of B, how I can write down f of AB. So this f of AB I can write down f of BA. So f of B into f of A I can write down. So B dash into A dash I can write down. So therefore R dash is commutative ring. So first condition is over. Now what we need to show, that second condition, without zero divisors. If R is a without zero divisors and R dash is also without zero divisors, we need to show that. So first of all we should know what is zero divisors, then only we'll get to know how we need to show that. Okay, so only the thing is we need to prove that A dash into B dash is equals to 0 dash in R dash, where A dash is equals to 0 dash or B dash is equals to 0 dash, I can say. Okay, so suppose if I take A dash belongs to R dash and B dash belongs to R dash and A dash into B dash is equals to 0, if I take, then there exists obviously AB belongs to R, such that how f of A is equals to A dash and f of B is equals to B dash, right? So now A dash B dash is equals to 0 dash implies f of A into f of B is equals to f of 0. Will get it by homomorphism, properties of homomorphism. I can write down f of 0 as 0 dash. So therefore f of AB is equals to f of 0, A into B is 0. See how they are given. So A is 0, B is 0, we are getting AB is 0. So therefore what is our conclusion? According to the zero divisors, what we have, A should be non-zero and B is non-zero, then A into B should be equals to 0. A is non-zero or B is non-zero, then AB is 0. We should get, but here we are not getting non-zero, we are getting 0. So therefore what I can write down, f is, sorry, R has no zero divisors, this one, R has no zero divisors, therefore f of A is equals to f of 0 I can write down, f of B is equals to f of 0 I can write down. Therefore this implies A dash is equals to 0 dash or B dash is equals to 0 dash. So this condition we are getting for every A dash is A dash B dash belongs to R dash, A dash is equals to 0 or B dash is equals to 0 dash, we are getting A dash B dash is equals to 0 dash. Therefore what we can say, that if R is having non-zero divisors, then R dash is also having non-zero divisors. So let us see third condition. So third condition is, if R is a ring with identity, then R dash is also with identity. So already you know that what is identity, right? So let R be a ring with identity element 1, then f of 1 belongs to R dash according to the definition, right? How they have defined the function, like that we need to take, right? So if one R be a ring with identity element, this one is an identity element that too belongs to what? Capital R. So if one is belongs to capital R, then I can write on f of 1 is belongs to R dash. So A dash belongs to R dash, we have taken. Obviously f of A is equals to A dash, I can write down for some value of A belongs to R, right? So f of 1 into A dash, what we are going to show that it is also having, R dash is also having identity element, right? So for that purpose, what we need to take means f of 1 into A dash is equals to what we have, what I can write down, f of 1 into f of A I can write down. So f of 1 into A, I can write down f of 1 into A. F of 1 into f of A, I can write down it as this one. So we'll get f of A. So again f of A is A dash. So this A dash acts as what here? Identity element. Got that? So similarly, I can show that A dash into f of 1 is equals to A dash, right? So here A star E is equals to what I should get? A only. So that condition E star A is equals to A only we should get. So that we are shown here. E star A is equals to A only we should get. So this E is what? F of 1 over here. Okay. So by observing these two conditions, we can say that R dash is a ring with identity element f of 1. Okay. So next we need to show that the fourth condition. If R is an integral domain, then R dash is also an integral domain. So integral domain, you should know the definition. So integral domain, according to the definition what we have, R must be commutative ring, first one. Next, R has no R has unity, that is what identity, and third condition is what R must have non-zero divisors, right? So then we can say that R is an integral domain. So if you observe about three conditions A, B and C, we can say that R dash is also commutative ring with identity and without zero divisors. Therefore R dash is an integral domain. Okay. So let R be a field. So we need to show that if R is a field, then R dash is also field, we need to show that. So field, according to the definition of field, R must be commutative ring with identity, and every non-zero element should have their multiplicative inverse. See here. So only the thing is, we need to show that every non-zero element of capital R dash is having multiplicative inverse. So therefore by first condition and third condition, right? So we have we can say that R dash is a commutative ring with identity, right? So now only the thing is, we need to prove that non-zero element in R dash has multiplicative inverse. So therefore if I take A dash belongs to R dash be a non-zero element, then obviously A belongs to R, because R is a field we have. So such that f of A is equals to A dash, I can write down. R is a field, right? A must be a non-zero. Why? Because every element, the third condition of field is what? Every non-zero element of capital R is having its multiplicative inverse according to the definition of field. So therefore R is a field over here, A must be non-zero, therefore so multiplicative inverse exists. So therefore A inverse exists, and if A inverse exists in R, then I can write down f of A inverse must be present in R dash. So F is a mapping from R to R dash. Therefore, we have got this one. So now, according to the condition of inverse, right? How we need to show that A star A inverse A star A inverse is equals to what we should get E, right? So here E value is f of 1 because f of 1 belongs to what? R dash, right? F of 1 acts as what? An identity element of R dash. So therefore only the thing is we need to show that A is, instead of A we need to take A dash, which is belongs to R dash, and A inverse is our f of A inverse. So f of A into f of A inverse, if I show that E is equals to f of 1, then this condition is over, right? So consider A dash into f of A inverse. So what I can write down A dash as, we have f of A over here. So f of A into f of A inverse. And now according to the homomorphism, what I can write down, f of A into A inverse I can write down. A into A inverse is nothing but 1, right? Why? Because R is a field, and R is a field means R is having identity. So that to what? 1 is an identity element. So therefore A into A inverse is 1. So f of 1, which is belongs to R dash. So therefore what I can write down, R dash is a field. Only the thing is we need to show that every non-zero element of R dash has its multiplicative inverse. Okay. So this is how we need to show that. So in the next video we are going to discuss cosets of an ideal. I will stop over here. Thank you.